Problem number 17. A box of mass big M is sliding to the right with velocity v on the frictionless table. A small pack of mass m over 2 slides frictionlessly inside the box. Initially, the pack is at the left wall of the block with a rightward velocity of 2v with respect to the table. After time t, the pack collides elastically with the right wall of the box. How much longer will it take until the pack hits the left wall of the box again? Solution for problem number 17. As can be shown by working in the center of mass frame during an elastic collision, the relative velocity of the two objects only changes in sign. Therefore, the relative speed remains the same, so the time until the next collision is also t, which is answer B, and that was solution for problem number 17. The following information applies to problems 18 and 19. Problem number 18. A uniform rod of length L and mass M is placed with its ends resting on two identical springs of spring constant K as shown. The rod is initially in equilibrium. If the rod is uniformly displaced downward and released from rest, what is the frequency f of its oscillation? Solution for problem number 18. If the rod is displaced down by distance delta L, then the vertical net force experiences is 2k delta L. This is just like a spring mass system where the spring constant is effectively 2k, so the angular frequency is square root from 2k over m, and thus the frequency is this one. That's answer D, and that was a solution for problem number 18. Problem number 19. Next, the rod is brought back to equilibrium. It is slightly rotated about its center of mass, then released from rest. What is the frequency f of its oscillation? Solution for problem number 19. If the rod is rotated by a small angle theta, the net torque of the rod is this one. The rotational form of Newton's second law is torque equal moment of inertia multiplied by angular acceleration. So it means that for such rod we have this equation or this standard equation for angular oscillation. From this formula we can find that angular frequency equal this one and the frequency equal this one. That's the answer E, and that was solution for problem number 19. Problem number 20. A uniform hollow sphere is initially at rest on a horizontal plane. The plane begins to accelerate horizontally to the right with the acceleration a. If friction is high enough to prevent the sphere from slipping, what is its translational acceleration? Solution for problem number 20. It's easiest to begin by working in the non-inertial frame of reference or plane. In this frame there is a fictitious force on the sphere directed to the left. This is why it's negative ma, effectively acting at its center. Taking torques about the contact point with the ground, we can find that moment of inertia, which is 2/5 mr² multiplied by angular acceleration equal torque, which is force of friction F multiplied by radius R. So it means that because we don't have any slipping, we have ma prime, where a prime, its acceleration, is our new frame of reference, equal force F, friction's force F, plus force of friction F. From other hand, because there are no slipping, we have alpha equal a prime over R, which means that from second equation we have force of friction equal 2/5 ma prime. And putting these expressions to third equation, we have a prime equal negative 3 over 5a. Now we can go back to our original frame of reference and find that translational acceleration equal a prime plus a, which is 2 over 5a. That's answer D, and that was a solution for problem number 20. Problem number 21. Amora and Bronco are given a long, thin rectangle of sheet metal. It has been machined very precisely, so they can assume it is perfectly rectangular. Using calipers, Amora measures the width of the rectangle as 1 centimeter with a 1% uncertainty. Using a tape measure, Bronco independently measures its length as 100 centimeters with a 0.1% uncertainty. Which of the following are closest to the relative uncertainties they should report for the area and the perimeter of the rectangle, respectively? Solution for problem number 21. Calculating the area involves multiplying the two measurements, and so the uncertainty in the area depends on the relative uncertainties of the inputs. Amora's 1% relative uncertainty dominates Bronco's 0.1%, so the result carries 1% uncertainty. It remains 1% because the area depends on each input to the first power. Calculating the perimeter involves adding the two measurements, and so the uncertainty in the perimeter depends on the absolute uncertainties of the inputs. Bronco's 0.1 centimeter absolute uncertainty dominates Amora's 0.01 centimeters, so the result carries his 0.1% uncertainty. Note that while the perimeter is approximately twice Bronco's measurement, the relative uncertainty is unaffected by this observation, so the answer is not 0.2%. So correct answer is B, and that was solution for problem number 21.